All right, Andre. He has amazing parties with champagne and pianos every single night, and his very soulful friend John is always present. Every night, John drives to his friend Andre's house and hits an average of 3.5 green lights. Apparently, John has been tracking this data. What is the probability that Mr. John Legend will hit more than 2 but less than 5 green lights? This is a problem that a former graduate teaching assistant of mine created. I like it. It's very good, although it was a couple years ago, so you may never have even heard of Andre 3000 and John Legend. He didn't include Legend in the problem originally as he delivered it, but I did because I am happy I figured out it's John Legend. But anyway, X in this case, we'll learn from before, modeled in another problem some issues which you could encounter if you don't label the things that you're given and quantify what you're doing, write stuff out. X equals the number of green lights. One of the reasons that I love models so much, probability models, is because they help me deal with my life. When I'm driving home, if I hit, I feel like I'm getting lots of red lights, I probably am. It's just I'm getting unlucky. I could have lots of biases there, confirmation bias, recency bias, a lot of fallacies to my thinking as well. And that's what's so beautiful about data, the analysis of data and probability models, is I can at least think to myself, all right, well, it's bad luck. It's just not my night, right? The idea being that, back to John and Andre, John's driving to Andre's house. Some nights he'll hit 6 green lights, red lights. The teaching assistant, I would have preferred red light, but I like this problem a lot, especially compared to that crap fest that was decades and, converting that. This is a bit easier, isn't it? Although it's more challenging and computationally, perhaps. All right. So the number of green lights that John hits, John Legend, as he goes to this party. Point out here the values that I like to call baby X can take on. Green lights. He could hit 0 green lights. Well, it'd be really hard to get to the party if he hit 0 green lights, right? Would take a long time. I mean, eventually the light's got to be green, right? So in order to continue, right, just consider, right, if you're arriving to the light and you're stopped, we'll call that not a green light, all right? But you can hit 0, you can hit 1, you can hit 2, and there's no boundary here for this problem. And again, that word average is just yelling at you, do Poisson. I'll stop writing here. Although I think it's helpful to write all these out because it's going to remind you that you're talking about a Poisson distribution without a bound. The rate on average is lambda equals 3.5. What's the probability that he'll hit more than 2 but less than 5 green lights? So this, unlike the other problem, which was deeply problematic for me, and it was a challenging problem with decades, all right? The sneezing one is, I think, pretty easy. This one is maybe more challenging as well because you have to do a couple things here, and you got to avoid a couple problematic situations, right? More than 2, that means that we're not including the 2, all right? So we want the probability that x equals 3, and this is the additive rule, or addition rule, from probability, but we want the probability x equals 3 plus the probability x equals 4. And less than 5, we're not going to include the 5. It's just the way it is, all right? We need to calculate this probability. So we could go to the table, which I recommend you do. Let's go to the table. The crinkling of papers is the dealing with tables. And we're going to go to where it has up top, it's going to say mu, which is the same thing as lambda. I've just used slightly different tables for you guys. All right, so I want to go to mu of 3.5, where it has all this business worked out. It's got all the probabilities. That's why I call it probability tables. It's got all the probabilities worked out for you. 3.5. So what we're going to do is we're going to go down to column 3, look at that probability, and then 4, look at that probability. And I'm getting this. So we have like mu over there. Let me 3.5, and then over here we've got like x. And we're going down to entries 3 and 4, and at 3 and 4. 0.2158. Woo! There's a lot of probability at 3. Why is that? Because that's close to the mean. That's going to be the highest point on the graph. All right, 4 is, I can remember that one, 0.1888. And then you're going to add these together, and bing, bang, boom, you have your answer. You also could use the formula, which I'm gonna. Here we go. I'm gonna use the formula, the PMF, probability mass function. It's telling you how much probability is at each value. All right, we're gonna take this and then add it to this. So I want x factorial, so that's 3 factorial, e to the negative 3.5. 3.5 to the third power. See, you can tell what order I've done these in. E to the negative 3.5, 3.5 to the fourth power. All right, and you're going to get. Let's jump over to one of our favorite websites. This one you're going to have to do for 3. Come on, be the same thing as what I have. Is it? It is. And then you got to do it for 4. Come on. Yep, there it is. You're going to add those together. Notice we're sort of creeping toward a approximate normal distribution here, right? Really good applet. Definitely check it out. And, yeah, check out the other problems as well, and use this to keep yourself happy when you're driving to parties.